So there could be some chances to find some indication of dark matter if it exists. So I will just say a few words about compact stars. We have been listening to many talks about it, and then I will go through selected scenarios like the cooling of neutron stars through axions, or neutron star collapse into a third family, combustion into strange stars, measures of neutron stars, primordial black holes that have already been discussed, and sexa quarks in compact stars. And yeah, and then I will just try to wrap up by mentioning some measurements that could probe dark matter in compact stars. So when we say compact stars, we know that these are very dense objects. So if we do just a very basic back of the envelope calculations, we can find that the normal or the mean density inside the heavy nuclei is about 2.3 times 10 to the 14 grams over centimeter cube. And if we compute using the same, let's say, the same approach to the where you consider the typical scaling of the atomic radius, just but this time we compute the density of a neutron star of about, let's say, 10 kilometers and a mass of solar masses, which is near the most massive observed neutron stars. Then we come with a number about 10 to the 15 grams per cubic centimeter. That's about 4 times saturation density. So we see that we learned that if the neutron stars were just homogeneous, they will contain density, matter compressed about at least 4 times saturation density. But in reality, neutron stars are complex. They are not homogeneous. They have a very rich structure, and in all of these regions, from the very thin atmosphere to the very dense core, there could be different states of matter and different phases or can be present. Like in this, like for instance, consider the cross-core transition, where it's expected to be some sort of nuclear pasta that appears because of the competition between the Coulomb and the nuclear forces. So because of this, whatever, if the modification because of the dark matter contact, there could be some indications. There could be some some signatures. So and because of this, I will discuss a few examples. Let me just say a few words about compact star sequences. We have heard a lot about the mass-rate relation. So this is very important and very basic, because the idea is that there's a 1-to-1 correspondence between the equation of the state that will correspond to the plot, to the left part of this plot, into the mass-rate relation that could be the right part of the plot, and the maximum mass of the neutron star is determined by the equation of the state. So since we are not completely certain about the equation of the state, so we don't know exactly what is the most massive neutron star out there. So as I said, the motivation is because now we have many observations and many nuclear experiments in colliders and some other different type of measurements. And also we have astrophysical detections, and there could be also related to transient energetic emissions, like we was heard today about gamma ray bursts or emissions of gravitational waves. So we want to look into these different channels to see if there's an imprint of dark matter there. So as neutron stars are very dense, so it's possible that in their interiors appears the confined nuclear matter. That means a state of matter where quarks and gluons are not located or localized into nucleons, but rather form some sort of plasma, the so-called quark-gluon plasma. And if we consider the phase diagram of QCD that is here, neutron star will be located at rather low temperatures, but very high densities. And even more, we can consider the third axis of this plot, where the isospin asymmetry it could be located. So compact star will be like located a bit out of the plane here in the ground. So it's a very rich, very how to say, very active field of study to try to understand the whole QCD phase diagram from lattice QC calculations to different effective models to heavy ion collisions that will take place in accelerators like in FAIR and so on. So as I said, we don't know the most massive neutron star. We don't know what is the maximum mass of neutron stars because it depends on the equation of state. So we rely on observations of very massive neutron stars to try to set up a constraint or a limit for this. There has been also mentioned that there are already some estimations that the maximum mass could be about 2.3 or something like this from the study of the mergers of GW170817. And but just consider, for instance, the recent neutron star measurement of this PSR J0952. The neutron star has 2.35 solar masses with some errors. So it's quite compatible to this max of estimates of the mass of the solar masses. And interestingly, this pulsar rotates at a frequency of 707 Hertz, which is the second fastest spinning pulsar known, and actually is located in our Milky Way. So this kind of discoveries really help for the understanding of the equation of state. So what happens if there's dark matter in compact stars? So let me go through several interesting scenarios. But first, let me mention that, as you probably know, there are many candidates and different searches for dark matter, depending that they range or they span a huge range of energies from very light particles that could, for instance, ultralight dark matter or pre-inflationary diaxion, which is one of the most, how to say, accepted or one of the most exciting candidates nowadays. Diaxion can be related to QCD because they are associated to the strong CP problem, which diaxion sort of cures it. And there are other ones that can be more massive, like hidden dark sectors or WIMPs or different other possibilities. And of course, even the black holes, the primordial black holes could be considered as dark matter. So there's a lot of ideas and there's a lot of efforts to try to disentangle what is dark matter. So back in the days in 2016, Armen Sedrakian had already looked into the effects of the cooling of neutron stars, but including axions. So basically, there was some effect because of the emissivity, the interaction with the axions, and then there was some splitting of the typical channels that were related to the pairing of the protons and neutrons, and these axions will have some effect. So if we see something like the surface temperature of a neutron star, and we consider each line corresponds to certain mass of a neutron star, so the deviations can be caused by this axion cooling. So this could be a smoking gun for the axions if they are there and they allow for, if they cool the neutron star, because the neutron star usually cools via photons and neutrinos, but in this case oxygens could also help for the cooling, contribute to the cooling. So as I said, there's a lot of motivation to consider the axion. So actually, I've been starting a collaboration with Marco Ruggeri and Gabriela Gurufel and the student of Marco Bonan, and we're starting to put some of these ideas, considering the potential of the axion, the QC axion potential, and see how it will modify dense matter. This is just a work in progress, so I cannot tell you so much right now, but I can tell you that what we have found so far is that under this scheme, only hot dense matter is the one that is affected by the properties of stars. That proton-neutron stars or the mergers that are hot are the ones that resembles more effects of these axions under this scheme. Thank you. Other approaches include the scattering of photons in the crust, scattering of dark matter in the crust, leading to phonons. So for this, you can look at this paper. They consider just collisions of dark matter into the crust, and there could be some oscillations that hopefully could be detected. We have heard already about primordial black holes the first day of the conference, so I will not tell too much. But if they exist, they might be out there, or they can even be trapped in neutron stars, and this could also lead to some observables. Yeah, this is, for instance, a paper of Professor Abramovich, so you have heard about it. Other possibilities that the neutron stars collapse into strange stars. This is following some hypotheses by Edward Witten, who considered that perhaps the state of matter that we are made of is not the most stable state. So if that's the case, and if somewhere in the universe strange quark matter exists, then when it goes into contact with regular matter, then regular matter will turn into strange matter. So in this case, if, for instance, some meteorite of strange quark matter, so the so-called strangelet, hits a neutron star, then the neutron stars will just consume into a strange star. I'm sorry, the strangelet hits the neutron star, and then it could end up being transformed into a strange star. So this is some calculations and event modeling by this group. The other idea that I like to consider always is the mass twins that present a third branch in the mass-radius relation, where one of the branches corresponds to a compact star with a phase transition into something. It could be quark matter, but let's imagine that quark matter doesn't appear in neutron stars. That matter doesn't not confine inside neutron stars, but instead dark matter is captured in the interior. So under certain conditions, this could lead to the third branches, to the hybrid compact stars, but not hybrid in the sense that they have the confined quark matter, but just regular matter with a dark matter core. And we have just considered a model like this, where the quark matter never confines inside neutron stars, and we just put some linear dark matter, and we can model this, or we can consider this scenario. Of course, this has some observables because of the tidal deformabilities. Consider, for instance, the case of GW170817. So if there are three branches, the lambda plot that corresponds to the tidal deformabilities will have different branches, and this corresponds to different possibilities. I will not discuss them here, but if you are interested, you can look at this paper. So the message here is that the lambda plot will have different lines that are not standard. So this could also be a smoking gun. Just recently this year, a group by Bruno Lopez and other collaborators like Veronica Desheimer, that have considered also actions inside neutron star, and they also found that the actions could destabilize the neutron stars and just will become unstable, or they could just collapse if under certain conditions. So this is also very interesting. So I'll leave you here the references. In the case of the twins, a transition from the hybrid star, from the pure neutron star into the hybrid branch, for instance, through capture of dark matter in their interior, could lead to a transformation which is associated to a energy release. So this could release some flare. So this is also interesting to consider. And I will try to wrap up, to go a bit quicker through this last part. So what if dark matter is bosonic? So if it is bosonic, there are different possibilities that the dark matter here depicted in black, it lies everywhere inside the neutron star and outside as a halo, or that the dark matter is just trapped in the core, or that is just distributed uniformly. And these authors have considered this possibility and consider a model where they solve two TOV equations, one for dark matter, one for the normal matter, and they have predicted different properties like mass radius. But in the case of the mergers, these three possibilities will have different imprints. For instance, if there are halos before the mergers, before the merger, they could have some imprint in the gravitational wave. And another possibility is a scenario that is, let's say, rather standard, but still feasible. Is the possibility of creation of sexaquarks. That these are like quarks that are like a baryonic state made of 6 quarks strongly bound. And we have considered this because the sexaquark could be a good candidate for dark matter from cosmological arguments. And most important, interestingly, is that it can be sought. It can be sought in heavy ion collisions. Therefore, we model neutron stars, and we found that there could be configurations that allow for this. And so this is also another possibility. So that's why we have computed this and brought some predictions. And just a few words before I finish, I would like just to remind that the other possibility is that modifications to neutron star are not produced only by dark matter, but also through alternative theories of gravity or dark energy. For instance, just consider the TOB with a cosmological constant. And you can see, for instance, in this paper that we wrote, how the cosmological constant could, if it affects the interior of neutron stars, how it could modify. So I think it's interesting or one should be very careful into looking into the constraints of neutron stars, and also check for the possibility of dark matter or rule out and dark energy, and try to look or to find something like that, or to rule out. So this is basically what I wanted to tell you. Thank you so much.